Hello friends, this is Professor Afaq Ahmed from Navi Mumbai, India. In this lecture, we will start a discussion about a nuclear power plant, or it is called as nuclear energy generation. Cheap and abundant power is essential to the modern world in coming years. The rapid increase in industry and living standards of a people creates the pressure on conventional sources of a power like coal, oil, and gas. It is now obvious that these sources will soon be unable to meet the demands of increasingly power hungry worlds. Again, this background, the atom at the first regarded as a symbol of destruction, offers an important source of prosperity. Man has now learned to draw the colossal power locked in the heart of atom and use of it for the beneficent and benefit of humanity. Today, the atom is considered as the almost limitless source of power, which has opened a new horizon to the mankind. One of the outstanding facts about a nuclear power is the large amount of energy that can be released from a source mass of active material. Complete fission of 1 kg of uranium contains the energy equivalent to 3100 tons of coal or 7000 tons of oil. The total amount of uranium and thorium in the Earth's crust to the depth of 5 kilometers is estimated approximately 10 raised to 12 tons. It is further estimated that the economically extractable ores are nearly 25 million ton of uranium and 1 million ton of thorium. The colossal power hidden in uranium and thorium represents a significant contribution to the world power resources. In India, the Tarapur, Rana Pratap Sagar, and Kalpakam nuclear power plants will be capable of producing 1200 megawatt of power, and it is proposed to double the output by expansion of these plants in a short period. Several states in India like Gujarat, Rajasthan, and Uttar Pradesh, especially in areas where thermal and hydropower plant cannot be set up due to long distances of a coal mining regions or lack of suitable sites for hydroelectric power generation, are looking forward to the possibility of setting up atomic energy stations. Presently, India has 19 operating nuclear power reactors. The present generation capacity is nearly 5500 megawatt, which is 3% of total energy generating capacity of the country. Power plant of 230 megawatt capacity working on a cycle of pressurized heavy water reactor, that is PHWR, already went to critical at Narora in Uttar Pradesh. The nuclear power plant at Kakrapar in Gujarat, this ISET, already went critical and second set also went critical. The okay, the adoption of nuclear energy for the generation of power is inv- inevitable to the nations where other sources of generation like fossil and hydel are inadequate and scarce like in Western Europe. The United Kingdom is an outstanding example of this, where presently the major sources of power generation is nuclear energy. The purpose of this article is not to discuss the importance of nuclear power at a particular country, but to find the economical adoption of nuclear power compared with the other sources available in the developing countries. The economic advantage of nuclear power can be realized only if can ensure a guaranteed baseload about 75%. The number of hydrochemical processes, fertilizer plants, desalination of water, and use of electricity for pumping water from tube well assure a constant baseload. Therefore, such type of power requirement must be developed before adoption of nuclear power in a country. For more videos, you can subscribe my channel. The channel is described here perfectly. It is meaningless for a country to talk of reliable solely on hydel or thermal or nuclear power. It is well known that the at least count cost of solution involves a grid in which there is a mix of all three types of generating units. This arises from special feature of hydropower which is the best for peak load and nuclear power which is the best for base load. The cost of generation by nuclear power is least when the load factor is maximum and the cost of hydropower is lower than the nuclear when it is used as a peak load station. The overall cost is minimum when there is a proper mix of hydro and nuclear. Then the next problem arises, what mix is the best for most economical operation of the national grid? The countries of the world are each planning their own courses of nuclear power development or decline. Nuclear power is competitive with the natural gas. It is non polluting energy. It does not contribute to the global warming. Obtaining the fuel only takes 5% of the energy output. Plant licenses have been extended from 20 years to an additional 20 years. Newer designs are being sought to make them more economical and safer. Pre approval of a few designs will hasten development. Disposal of high level radioactive wastes still being studied, but scientists believe deep burial would work because they are have large electrical output. Their cost at $2 billion is hard to obtain and guarantee with banks. Replacing plants may be cheaper using the same sites. A developing country like India generally faces many problems while initiating nuclear power program in a view of various limitations involving technical, economical and national considerations. The most important bottleneck in India's nuclear power program today is a shortage of trained scientists and engineers with experience to take over independent responsibility for a design, construction, and operation of nuclear power plant. India presently has about 2500 trained scientists in 1975 and engineers, but if squarely responsibility is to be shouldered with indigenous material and design to build atomic power plant for future, India has to pass a long way to train more number of people to the shoulder this responsibility. In this slide, you can see the total supply of nuclear energy at a global level is around 4.8% only. That is, we need to harness more energy by means of a nuclear power. Now, this is the top 10 nuclear energy generating countries. The first is starts with United States of America, France, then Russia, then Korea, China, Canada, Germany, Ukraine, United Kingdom, and Sweden. These are the top 10 nuclear generating countries, and this data has been conducted and collected in year 2013. Some neutrons may escape from the core without absorption and will be lost ever. This material is called as a reflector. The required properties of a good reflector are low absorption and high reflection for the neutrons, high resistance to oxidation and irradiation, as well as high radiation stability. Many times, the material used as a moderator is also used as a reflector because the moderating material have good reflecting characteristics. The H2O, D2O and carbon are used as reflectors. The amount of fissionable material required can be reduced with use of good reflector. It is necessary to provide some method of cooling the reflector as it gets heated due to collision of neutrons with its atoms. Next component is coolant. The main purpose of the coolant in the reactor is to transfer the heat produced inside the reactor. The same heat carried by the coolant is used in the heat exchanger for further utilization in the lower generation. Some desirable properties of a good coolant are listed here. It should not absorb the neutron. It must have high chemical and radiation stability. It must be non-corrosive. It must have high boiling point if liquid and low melting point if solid. It must be non-oxidizing and non-toxic. Next component is control rods. Some type of control is absolutely necessary to fulfill following functions. First, to start the nuclear chain reaction, when the reactor is started from cold, the chain reaction should be maintained at steady state condition at required level to shut down the reactor automatically under emergency condition, that is, a pump circulating the coolant through the reactor fails. The control is necessary to prevent the melting of a fuel rods, disintegration of a coolant, and destruction of a reactor, as amount of energy released is enormous. The control of chain reaction is possible either by removing the fuel rods or neutrons continuing the chain reaction from the core of the reactor. It is always easy to get rid of the neutrons. It is generally done by inserting the control rods into the fuel tubes. Next part is called as the shielding. The reactor is a source of intense radioactivity. As mentioned earlier, these reactions are very harmful to the human life. The common radiations from the reactor are alpha, beta, and gamma rays and fast neutrons. To prevent the effect of these radiations on human life, it is necessary to absorb them before emitting to the atmosphere. Neutrons and gamma rays and all other radiations are effectively absorbed by the concrete and steel. Next part is reactor vessel. The reactor vessel includes the reactor core, reflector, and shield. It also provides the entrance and exit passages for directing the flow of coolant. The reactor vessel has to withstand the pressure as high as 200 bar or above. The holes at the top of the vessels are provided to insert the control rods. The reactor core, fuel, and moderator assembly is generally placed at the bottom of the vessel. So these are the basic components of nuclear reactor. So here the components have been enlisted: fuel, moderator, reflector, coolant, control rods, shielding, and reactor vessel. Now see how the nuclear energy comes from fission. Okay. Nuclear energy is either completed from fusion or fission chain reactions. In this reaction, first we'll study fission chain reaction, or it is called as nuclear fission. When unstable heavy nucleus is bombarded with high energy neutrons, it splits into two fragments more or less of equal mass. This process is known as nuclear fission. Here in this diagram you can see the neutrons are bombarded on uranium atom, which splits this atom into two. The fission fragments formed due to fissions are the isotopes, which are located in the middle of periodic table. The binding energy per nucleon for the element in the middle range of periodic table is more than middle range of periodic table is always more than that of heavy nuclei. Therefore, the nuclear fission is always associated with release of large amount of energy. Further, nuclear fission is allowed by the emissions of several high energy neutrons per neutron bombarded. This is the essential condition of the self-sustaining the fission reaction. Self-sustaining nuclear fission reaction associated with release of energy is very important in the power development. To sustain the fission processes, the following requirement must be fulfilled. First, the bombarded neutrons must have sufficient energy to cause fission of another nucleus. The number of neutrons produced must be able to increase the rate of fission at certain loss of neutrons by absorption and leakage is unavoidable. The fission process must generate the energy. The fission process must be controlled. Here, the conversion of nuclear fission chain into the heat, and this is the general layout of nuclear power plant. Here we are getting the heat from the nuclear fission reaction, and which will be used to produce steam from the water, and this steam is supplied to the turbine, wherein the turbine will rotate and it is directly coupled to the generator, which generates or creates an electricity. Now, types of reactor. First reactor is PWR. Okay, in this type of reactor, enriched uranium is used as a fuel and water is used as a coolant. Moderator and reflector like PWR, that is pressurized water reactor, and this BWR stands for boiling water reactor. So the reflector like PWR accepts the steam is generated in the reactor itself instead of separate steam boiler. The arrangement of this single circuit is shown here. The majority of power plant in United States of America are of PWR and BWR types, as diffusion plants are established for enrichment of a fuel during Second World War. So in this reactor, the boiling water reactor is more stable than pressurized water reactor and much stable than any other type of reactor, as increase in the reactivity increase the steam formation and reduces the hydrogen content per unit volume. The reactivity automatically is reduced as vapor is not dense enough to moderate the neutrons efficiency, and effectively the reactor goes subcritical. Therefore, the BWR is known as self-controlled reactor. The main disadvantage is the boiling water reactor cannot meet a sudden increase in power demand, because as the power output of the turbine increases, the pressure in the reactor falls and the specific volume increases. The steam bubbles within the reactor would expand, expel the moderator, and tend to shut down the reactor. Therefore, unless it is properly designed, the boiling water reactor might have negative power demand coefficient, so that when more power is demanded from the reactor, it may produce less. Next is PWR, that is pressurized water reactor.
The arrangement of pressurized water reactor is shown in this diagram. In its simplest form, a pressurized water reactor is light water cooled and moderated reactor. It uses enriched uranium as a fuel. The pressurizing tank included in the circuit maintains the constant pressure in the circuit throughout the load range. Electric heating coil in the pressurizer boils the water to form steam which is collected in the dome as shown in figure and pressurizes the entire coolant circuit before starting a reactor. To reduce the pressure, water spray is used to condense the steam. The fuel which is generally used is UO2. The uranium oxide is highly resistant to irradiation damage and it is very well adapted to high burn ups. It also highly resistant to corrosion by high pressure water in the event of breakup in fuel cladding. The water in primary circuit gets heated by absorbing the fusion energy in the reactor core and same energy is given in the heat exchanger to generate the steam. The water coming out of the heat exchanger is circulated. The water coming out of the heat exchanger is circulated by pump to maintain the pressure in the circuit in range of 100 to 130 bar. The water becomes radioactive in passing through the reactor. Therefore, the entire primary circuit including steam generator, that is heat exchanger, must be shielded to protect the operating person. The radioactive coolant does not make the steam radioactive in the boiler. Bezanov first is the first commercial nuclear stations in Switzerland working on PWR. Next is CANDU reactor. The reactors are more economical to those nations which does not produce enriched uranium as the enrichment of uranium is very costly. It takes a lot of money and liquidity to convert and enrich the fuel. In this type of reactor, the natural uranium, that is 0.7% of uranium 235, is used as a fuel and heavy water as a moderator. This type of reactor was first designed and developed in Canada. The first heavy water reactor in Canada using heavy water as a coolant and moderator of 200 megawatt capacity with 29.1% thermal efficiency was established at Douglas, Ontario, known as Douglas Power Station. The arrangement of the different components of CANDU reactor is shown here. The coolant heavy water is passed through the fuel pressure tubes and heat exchanger. The heavy water is circulated in the primary circuit in the same way as the PWR and the same steam is raised in the secondary circuit, transferring the heat in a heat exchanger to the ordinary water. The control of reactor is achieved by varying the moderator level in the reactor and therefore the control rods are not required. For rapid shutdown purposes, the moderator can be dumped through the very large area into tank provided below the reactor. Next is fast breeder reactor.
First we'll see what is breeder reactors. Nuclear fuel burn up and mechanism of breeding. It is already mentioned earlier that uranium 235 can be fissioned by slow neutrons ejecting on an average of 2.5 neutrons to maintain further chain reaction. Among the 2.5 neutron ejected, 1 neutron is used to maintain the steady state chain reaction. Among the remaining 1.5 neutron, 0.9 neutron is captured by uranium 238 and zero point 0.6 neutron is absorbed by the coolant, moderator, structural material and remaining escape from the reactor. The absorption of neutron by 238 uranium converts uranium 238 to plutonium 239, which is a fissile material as mentioned earlier. In fast breeder reactor, as enriched uranium or plutonium up to 10% is kept in the casing without moderator. The casing is surrounded by fairly thick blanket of depleted fertile uranium. The ejected excess neutrons are absorbed by the fertile blanket and it converts into fissile material. The heat produced in the reactor core is carried by the liquid metal. The arrangement of this reactor is shown in this diagram. This is a Fermi fast breeder reactor located at Laguna Beach, Detroit, Michigan in United States of America. It is the first fast breeder reactor in the world. Enriched uranium was used as a fissile fuel and depleted uranium as a breeder material. The total power output was 94 megawatt electrical as efficiency of 31.3%. The major advantage of fast breeder reactor is high energies. A structural material of a reactor do not absorb neutron, therefore a wide choice of constructional material is possible. The major difficulty is to remove the large quantities of heat from the core as the power density as high as 340 kilowatt per liter of a core volume, which is 40 times greater than CANDU type, 13 times greater than BWR and 200 times greater than gas-cooled reactor. Therefore, special coolant and special arrangements are necessary to carry out large quantity of heat. This technology is not adopted by United States of America and United Kingdom and Germany, as these countries are saturated with energy generation as per capita consumption is as high as 10,000 units against 550 units in India. In these countries, interest in FBR was given an impetus with Middle East oil crisis in 1970s, when both oil and uranium prices increased sevenfold. Presently, the scenario is changed. Uranium prices are back to old level. North Sea oil has become a new source of Europe. In, in the US, the new gas sources have been discovered. The Germany has a new gas pipeline from Russia. Therefore, they have no need of or no need okay to recycle plutonium in the fast breeders. The plutonium is a dual fuel as it is used in a nuclear bomb as well as the power generation if FBRs. Therefore, there are very and it is also fear of proliferation because FBR produces more plutonium than it consumes. But with fast breeder program like India,
one can use excess plutonium for power generation. That is the reason we talk about double time, that is, the time required to build one more reactor using the excess fuel produces from an operating FBR. Before getting concluded this chapter, I want to tell you certain power development in India and power station about a nuclear power development. Tarapur Atomic Power Station. The Tarapur power plant is India's first atomic power plant, situated 65 miles north of Mumbai. The site at Tarapur on the Arabian Sea coast was selected in August 1960 by Atomic Energy Commission after detailed investigation of various locations to determine the availability of adequate cooling water, foundation, health and safety condition, power transmission possibilities and other facilities as transport and so on. It is one of the largest power station in India. It consists of two boiling water reactor of equal capacity with total generating capacity of 380 megawatt. The choice of boiling water reactor was used. Enriched uranium is a preference to the natural uranium reactor has been determined by financial considerations. The most quoted by the British for building the natural uranium plant was much higher than the American quotation for enriched uranium plant. The other cause of selecting BWR was availability of a loan from United States of America on extremely favorable basis. Tarapur nuclear power plant is considered a dignity for India because this is the first reactor in the world which is continuously working for at least 40 years and present generation is 50% of its total original. It worked for 1,91,000 hours, generating 57 into 10 raised to 9 units by both reactors. Even during 2000, it has generated 247 into 10 raised to 7 units. Two more nuclear reactor phase 3 and phase 4, that is PHWR type, each of 540 megawatt capacity, indigenously designed and commissioned in December 2004, which supplies power 39% to the Maharashtra, 19% to the Gujarat and 17% to the MP and Goa. Two more reactors, each of 1000 megawatt capacity, stage 5th and stage 6th unit, going to be commissioned by the end of 2010. With this 3300 megawatt, the Tarapur is going to be considered atomic hub for India. Next is Rana Pratap Sagar Atomic Power Station. This is the second atomic power plant of India which works on CANDU type principle. This power plant consists of two identical units of 200 megawatt each. The first unit achieved its criticality in 1973 and second unit went critical only in 1980 due to material decay and delay and technical difficulties. The station is delivering 400 megawatt power. The station lies on the bank of Rana Pratap Sagar lake formed between two dams, Gandhi Sagar Dam upstream and Rana Pratap Sagar Dam downstream of the Chambal River. The station is 64 km from the Kota city and occupies an area about 8 hectares. The station is intended to operate as a base load plant. The power will be delivered to the Rajasthan grid. In addition to this, provision has been made to supply 15% of generated steam to the heavy water production plant as process heat, which is close to the reactor site. So, I'm going to conclude my lecture. Thank you very much for listening this lecture. For more videos, you can subscribe my channel that is indicated here. Thank you very much.